So we are here to do the math assignment with my teammates Yazid and Ameya. We choose the Gauss elimination system because it was the subject where we had the most difficulties. So solving three variables, three equation linear system is more difficult, at least initially, than solving the two variable systems because the computations involved are more messy. You will need to be very neat in your working and you should plan to use a lot of scratch paper. The method for solving these systems is an extension of the two variables solving by addition method. So make sure you know this method well and you can use it correctly. Fourth, the method of solution is based on addition and elimination. Trying to do actual additions tend to get very messy. So there is the solution, the estimates method for solving three or more variables systems. This method is called Gaussian elimination. So with the equation ending up what is called the row echelon form. This was one definition about the Gauss elimination system.
So after Raf's explanation about what are the bases and what is the Gauss elimination method, we will try to explain you an example of this. So we choose this matrix composed by 3 rows and 4 columns. The main objective of the Gaussian elimination method is based on the identity matrix that is composed by a diagonal of ones and full of zeros. To explain a little bit, is this one, the one in green. So the one here is reflected as Z, is the result of Z. So if you have a 1 here, the result here is the Z1. Then the one here is the one here reflected the solution of y, and the one here reflected the solution of x. So to begin with, like I was saying, we choose this matrix 1 minus 1 minus 4 3, 2 minus 3 4 14, and 0 2 8 0. So firstly, the black matrices are the solutions, and the ones written in red are the operations to make the solution. So first we have called like the first row F1, the second one F2, and the third one F3. So to begin with, we have, like I was saying before, the Gaussian elimination method is based in the identity matrix. So we have already a 1 here, and then what we're supposed to do is to have 0 and 0 in this column, in the rest of the column. So we have multiplied the first one, F1, by minus 2. So when you multiply F1 with minus 2, it's minus 2 plus 2 and 8 minus 6. And then we add it to the second row, that is F1 plus F2 reflected here. So it's 2 minus 3, 4, 14, and the result is 0 minus 1, 12, and 8. Then we wrote our new matrix after this operation that was minus 2, F2, and F1 plus 2. That results to this matrix that is 1 minus 1 minus 4, 3, 0 minus 1, 12, 8, 0, 2, 8. Now we have this column composed by 1, 0, 0 as the identity matrix 1. And then what do we have to do in this side of the matrix, in this one? We have to have a 1 here and 0, 0. First, as we can see, is a negative 1, so what we have to do, we have to multiply this row by minus 1 to have a positive number here, that is 1. So when you multiply this, it's the same matrix, just multiply this, the second row, F2, by 1. So we have 1 minus 1 minus 1 minus 4, 3, 0, 1 minus 12 minus 8, 0, 2, 8, 0. We haven't changed anything unless the sign of the second row, multiplying by minus 1. So now we have a 1 here. What we're supposed to do is to have a 0 here and a 0 here. So first, to have a 0 here, what do we have to do? Basically, we have to add the first row to the second one, F1 plus F2. That is, this operation here is here, F1 plus F2, 1 minus 1 minus 4, 3, 0 minus 1 minus 12 minus 8, that we have then this result, 1, 0 minus 16 minus 5. And the second step is to have here a 0, in this 2. So to have here a 0, what do we have to do? We have to multiply the second row. So 2 multiplied by f2 minus f3. That is the third row. This operation is reflected here. There is 0, 2 minus 24 minus 16. When you multiply the second row by 2, and then you subtract the row 3. That is 0 minus 2 minus 8, 0. This result is 0, 0 minus 32 minus 16. And then you wrote your new matrix composed by this and this. So this one is the new first row. Here, 1, 0, minus 16, minus 5. We keep the second one, because we had like the 1 here, so we keep it as it was. 0, 1, minus 12, minus 8. And we wrote our new row number 3, that is 0, 0, minus 32, minus 16. Then, after that, what do we have to do? We have to have here, in this column, the third column, 0, 0, and 1. So first, we divide this by minus 32 to have here a 1. Dividing this by minus 32, we come to this result. There is 0, 0, 1, 0.5. And then, what do we have to do? We have to have here a row full of 0 and 1. So 0, 0, and 1. And to change this to 0, we have decided to put F1, that is row number 1, plus 16 F3, that is the row number 3. And then for the second row, to have here a 0, we decided to put like F2 plus 12 F3. That is this one.
As Yazid just told us before, in the last column here, we're trying to look for a 0, 0, and 1. We already have a 1, but in order to get minus 60, in order to get 0 and 0, we have to do the following exercise. We need to do f1 plus 16 f3 first, which is this one over here. So f1 plus 16 f3, this is the whole computation. The final result is 1, 0, 0, 3. Now, for f2 plus 12 f3, this is the computation, and the final result leaves us with 0, 1, 0, and minus 2. So now when the following operations are carried out and completed, it gives us the following answer, which is what we were looking for. We have the identity matrix and the following values for our x, y, and z variables. So from the following computations, we realize that x is equal to 3, y is equal to minus 2, and z is equal to 0.5. And we have the identity matrix, so it is now solved. So now I'll be talking a bit about the real-life applications of the Gauss-Jordan elimination theory. So the first application is its use in fingerprint imaging. So Gaussian elimination is used to filter out noise in fingerprint images. It's also used in many types of coding, such as block coding, computer coding, etc. Another big use of the Gauss-Jordan elimination theory is its use to schedule algorithms. They use the Gauss-Jordan elimination theory to fix problems with parallel processing that they have in computers and to schedule algorithms according to their needs and requirements. So in conclusion, the Gauss-Jordan elimination theory has many applications in real life, and it's not only restricted to numbers and figures, but it has many real life applications, as I've just explained.